short word. A short word on Isabellenhütte company. It's a very old company, 500 years old. It's one of the oldest companies in Europe, actually. We do 3 different product lines, alloys, components, and shunt-based measurement systems. And I'm working for the latter of those product lines. And this is also what this webinar will be about. It's shunt-based current sensing with delta sigma modulation in inverters, the next step in phase current measurement. The goal that we have with that webinar is to explain the advantages of digitizing the sensing signal directly in the sensing module. So the goal is also to create a better understanding for everybody why delta sigma modulation and the technical requirements of designing the interface between a shunt-based current sensor and the customer control boards have advantages. Our agenda for today will include 4 different topics. First, we're going to have a technology overview. Then we're going to look into the delta sigma modulation principle a little bit more in detail. And then we will finally look at a showcase measurement demonstration. Last but not least, we will have roughly about 10 minutes to do some questions and answers. So we will read some of the questions that came up during this presentation. Jumping right into it, technology overview. The traditional solution to detect current in inverters is usually done by CTs, by current transformers. Those current transformers are usually located in between the IGBT current converter circuit, which you can see right here. I hope everybody's able to see my mouse too, and the electric drive right here. And the phase current detection takes place right in between. Usually what you do is you measure all 3 phases. As those CTs are inherently isolated, the signal can be directly used on your control board. It's usually a voltage drop signal that comes out of those CTs. You have to keep in mind, though, that what you can see in this blue box right here, that is what you have to do to basically convert this analog output signal into a readable digital signal for your control board. So what you usually need is a gain amp, a low-pass filter to filter out interference, and some kind of AD conversion to get out a readable digital signal. If you have a second stage comparator in here, you're also able to get an overcurrent signal out. The AD conversion allows to also synchronize the 3 phases of the measurement that we see here. So synchronization can be realized through the AD conversion die that you use. As a summary, CTs provide intrinsic isolation. They usually come with an analog output. They're affordable and have a compact footprint, depending though on the specific product and nominal range. Average to high accuracy depending on the technology, and overcurrent detection is possible through a comparator. There's also some challenges with those products. Usually you get interference by external fields, you get pseudo signals, offset errors, measurement errors that you have to deal with. You have hysteresis effects through external fields and overmodulation, which can cause a shift of the characteristic curve of those products. System inherent noise depending on the technology, especially with open loop and flux gate sensing modules. Coupling capacities between primary and secondary circuit, and accuracy depending on the temperature that the module sees and the location where it is installed. If it is somewhere where strong magnetic fields, for example, can occur. Now let's have a look at the shunt-based current sensing solution. The shunt-based current sensing solution is basically located in the same spot like the CTs, which makes sense because you want to measure the three phases of your IGBT or the three current phases that come out of your IGBT current converter circuit. So they're located right here too. The difference is though, as we deal with a resistive measurement principle here, so we measure a voltage drop over a very low ohmic resistor, those modules have to be integrated into the circuit. Means you physically have to open your circuit and integrate those modules onto the current bus bar. A major difference to the CTs though is that the output signal that you get is already digital. So those shunt-based current sensing modules will give you a digital output signal that doesn't have to go through any AD conversion anymore and can be directly used on your control board. Also, those current sensing modules already come with an isolation layer on the board. So an internal isolation means no additional isolation needs to be done in order for you to use the signal. Now, the signal that you actually get out, or let's start differently, the signal that you put in is an amp clock, right? Like a fast amp clock, in that example, 20 megahertz, and you will get a 1-bit data stream out of this sensing module with the same frequency. The advantage here is that it is easy for you to synchronize those modules by simply sending the same amp clock to all three of those modules. And like this, they're already synchronized. Now, the 1-bit data stream that comes out of those modules has to go through a decimation filter. This is because you kind of want to know an actual value that you measure. So you have to use filters to get this actual value for your control board. This can be easily realized either with a prefabricated die, like for instance, the TI AMC 1210, or on one of your CPLDs or FPGAs. Also, through the decimation filters, you're able to do overcurrent detection. To summarize that, shunt-based current sensing modules also come with internal isolation. Against a pretty widespread public opinion, it is possible to isolate those current sensing modules internally. In our case, or in that example, the galvanic isolation is up to 1.5 kilovolts. They come with a digital output. They're affordable and compact in footprint, especially if you look at measurement ranges above roughly, let's say, 500 amps. They have a high accuracy and a low offset over the current and temperature range. They provide a fast digital overcurrent detection possibility, and they're immune to magnetic interference because they provide a digital output signal right from the beginning, and they're based on a resistive measurement and not on an inductive measurement. There's challenges though. We also deal with coupling capacities between primary and secondary circuit, as with all isolated applications. We have to convert the 1-bit data stream, and this is actually going to be explained in the second chapter. And we have to mount those products directly on the bus bar. Now, let's have a look at a schematic diagram of a shunt-based phase current detection module. So, the basic component of this module is obviously the shunt itself, which is the light gray area here where you can see the two shunt legs. Those are usually copper shunt legs. And then in between, which is covered by the gray box right now, you would have the resistive alloy that actually measures the voltage drop. In this gray box right here, this is where the measurement electronics sit. So you would have an isolation layer right here that basically separates the high side up here from the low side down there. This isolation, as mentioned before, is in our example here up to 1.5 kilovolt DC, which is the highest rating according to DIN EN 6664-1-2008-01. We have a transformer here, a DC-DC transformer to provide power to the high side. And then we have another low-pass filter directly here at the sensing location, again, to reduce interference, which puts the still analog voltage drop signal right here into the delta sigma converter. On the low side, we have the connector that provides the power supply, and that also has the interface for the signal transmission right here. In our case, we use either TTL or differential signals like RS422 or LVDS. Obviously, with those shunt-based current sensing modules, the biggest challenge is to deal with accuracy too. It's all about accuracy. So there's a ton of parameters that actually influence on the accuracy of such a measurement system, such as offset error, amplification error, noise, dissipation power, long-term drift, linearity, temperature, parasitic disturbances, and disturbances through inhomogeneous materials. Now, it is important that we have procedures to keep those the influences of those parameters low. So, for instance, offset and amplification error are done right through a calibration line within production. Temperature calibration is done with a 2-point temperature calibration also within production already. We make use here of defined characteristics of the resistive alloys that we use. Dissipation power. We usually use low ohmic shunts here. A typical resistance would be 20 microohms, for instance, so dissipation power can be kept low. Usually, one deals with long-term drift by stabilizing the shunt during the production process. Means an aging process is applied to the shunt to make sure that its characteristics are stable. In terms of linearity, we have an advantage here because we actually look at a resistive measurement here, which is based on Ohm's law, which is a linear law already. So the overall behavior of those shunt-based current sensing modules is already pretty linear. But apart from that, we would choose an ADC with a high linearity as well. Noise is dealt with by choosing an ADC with a favorable SNR, a signal-to-noise ratio. Parasitic disturbances. Shunts are designed to have low inductivities. So as the shunt is a current conductor, it obviously has a magnetic field around it. And that magnetic field also induces currents in the shunt itself. So it's important by choosing a geometry, an appropriate geometry, to keep those inductivities in the shunt low. And last but not least, we use special resistive alloys in combination with copper to avoid thermoelectric voltages. So the copper legs are welded to the resistive alloys that is located in between those copper legs, which is a very good combination to keep contact resistances between those interfaces as low as possible. To summarize this first chapter, shunt-based current sensing solutions can have galvanic isolation of up to 1.5 kilovolts DC. They come with a digital output signal, and they have high accuracy combined with low power dissipation. Going into the next chapter, we will now talk a little bit about the delta sigma modulation principle. So what we did here, we visualized a first-order delta sigma modulation. There's obviously higher delta sigma modulation orders, but to keep it simple, we're going to look at a first-order delta sigma modulation. On the left-hand side, you have the analog input that comes from the sensing location, which is basically a small voltage. This is put onto a differential stage with the negative feedback of the DA converter down here. This stage is also called the adder or the delta of the delta sigma modulator. This value is put onto an integrator after that, which sums up the previous value and the current value. This value again goes into a comparator, which compares it to 0. So if this value is larger than 0, it will put out a 1 or a high bit. If the value is smaller than 0 or negative, it will put out a 0. So at the end, you will get a 1-bit sequence here, a sequence of 1s and 0s that comes out of this loop with the frequency that you trigger it. In our example, this will be 20 megahertz. Now, the DA converter down here will output either a positive reference voltage if we have a high bit here, or it will output a negative reference voltage if we have a low bit, a 0. Now, what is important, you would always choose your reference voltage according to the maximum or minimum of the actual measurement range that you're looking at. So for instance, if you look at a measurement range of 500 amps plus minus, you would put your reference voltage accordingly. So it fits obviously to the input voltage and your gain amp that you use. So yeah, summarizing that one more time, the mean value of the 1-bit data stream is equal to the input signal's mean value. Means like all those 1s and 0s, if you average them with and multiply them with the reference voltage, you will get an average of the analog input voltage. Now, the delta sigma modulator outputs this 1-bit data stream, but how is that actually linked to the analog current value that we actually want to measure? So this picture right here tries to illustrate that a little bit. You can see the 1-bit data stream right here, which indicates a low bit down here and a high bit up here, and you see you get like the sequence of lows and highs, and if you overlay that with the analog current value to be measured, the green line right here, you would see the following. You would get the negative end of your measurement range. In our example, minus 500 amps, if there's only a sequence of zeros in the 1-bit data stream. On the other hand, you would get the maximum positive current measurement range, so plus 500, if there's only ones in the 1-bit data stream. And accordingly, if you're right in the middle at 0 amps, you would get a sequence of 1s and 0s. Now you could ask the questions, what are your arguments for actually using delta sigma modulation? It gives you flexibility in filter architecture and parameter settings. This is something we will have a closer look on in the next chapter. It gives you a digital image of an analog value right away. So there's no in-between processing necessary, which is an advantage, as we mentioned before, because you're immune to magnetic fields, because you deal with a digital value right away. Simple synchronization of all modules through equal frequency of the M clock input. And last but not least, it's a cost-efficient solution for the targeted applications. Now, the interesting part is, how do I actually convert this 1-bit data stream into a readable digital value? Simply put, the 1-bit data stream's mean value equals the current measurement, as we mentioned. The challenge is actually, or what's the interesting part now, is how do we actually convert this 1-bit data stream into a readable digital value, right? So Simply put, the 1-bit data stream mean value equals the current measurement. This is what we heard before already. So in other words, the 1-bit data stream shows the desired information in the lower and slower part of its spectrum. That information is overlaid by interference though. So what does that mean? That simply means we need a low-pass filter to actually get a readable value. So the simplest form of a low-pass filter is the mean average, because the frequency is obviously reduced by averaging the values. There's more complex and accurate forms of low-pass filters around though, sinc filters. And we will have a closer look at the behavior of those sinc filters now. So what we did in that slide, we basically simulated a rising edge current, which is shown right here in the turquoise line. And what you see in this graph right here is on the x-axis, you see the time in microseconds, and on the y-axis, you see the arbitrary current value. So this is a perfectly simulated rising edge. It won't occur in real life like this, but we just did that to show how a sinc filter behaves in comparison to a simple mean average. Going further down the time axis here, you can see we did a zoomed in window here, and we actually overlaid this rising edge current with a more or less realistic noise right here, the turquoise line. Now, looking at the mean average, we chose a mean average with an oversampling rate of 512, so it's 512 values. Now, with an input frequency of 20 megahertz, that actually gives us a delay of 25 microseconds until we actually see the rising edge right here. And then once we actually see the rising edge, we can see the mean average kind of oscillates around this current signal right here. So it's not ideal. We could increase accuracy here by simply increasing this number, the oversampling rate. But for instance, if we would increase that to 1024, we would end up at 50 microseconds until we finally reach the rising edge current here. Now, this can be made more accurate by using sinc filters. So, for instance, we show a sinc 3 filter here with an oversampling rate of 128, and you can see the sinc 3 filter reaches the rising edge current a lot faster. So after 10 microseconds, more or less, we already get a value that shows pretty accurately this arbitrary value of 0.9 that we have here. The difference is, though, as the sinc filter uses an oversampling rate of 128, you get a signal every roughly 3.5 microseconds or something, while the mean average gives you the full 1-bit data stream frequency back, which is, I think, 20 values per microsecond. And you can see that. So the mean average will give you a lot more values, but the sinc 3 filter is a lot more accurate, and a signal every 3.5 microseconds is still pretty fast. So sinc filters, which are part of the SI filter group, can be used as a digital low-pass filter for the 1-bit data stream, while the simple arithmetic mean is not that suitable for the simple fact that it is slow, like it takes time until you actually see such a rising edge current. Now, I mentioned before with those sinc filters, we actually have different degrees of freedom that we can change according to what our needs are. Now, in this graph here, you can see we have depicted the sinc filter behavior independent of the oversampling rate here on the x-axis and the ENOPS, the effective number of bits, here on the y-axis. Now, if you look at a sinc 1 filter, a first-order sinc filter, and we take our example with the oversampling rate of 128, which would be roughly here, where my mouse is, you would get an ENOP of roughly 8 bits. Means like the other 8 bits of your 16-bit signal would be noise, more or less. If you increase the filter order, though, and you look at a Sync 2 and Sync 3 filter, with an oversampling rate of 128, you would already get an ENOP of 14. This can be theoretically increased to the full resolution of 16 bits, but you can see you have to go pretty high with the oversampling rate to eventually get there. So the conclusion is the higher the oversampling rate, the higher the ENOP, the effective number of bits, but the lower the data output rate. Summarizing this second chapter, delta sigma modulation is based on a 1-bit data stream. Digital filters are used to convert the 1-bit data stream into a readable digital value. Oversampling rate and filter order can be used to fine-tune the output rate and the ENOP. Now we're coming to our third chapter in this presentation, which is our little measurement showcase. We recorded the major part of this measurement showcase beforehand because it was just too complicated to let the test setup run while we're actually on WebEx. So that would have caused probably another blackout here. So so we recorded that beforehand. So I will explain the test setup, and then we will look at a short video to actually see the test. So we chose a shunt-based current sensing module right here, which works with a 20 megahertz clock frequency to be triggered. And this current sensing module was fed with a 9-volt, 50 hertz grid current frequency current that it had to measure. Then we used an evaluation kit that contains different filter orders, Sync 1, Sync 2, Sync 3, and Sync Fast, together with a PC software, a readout software, to actually show or plot the actual current that we measure. And this evaluation kit basically interferes with the current sensing module by sending the M clock signal to the sensing module, and it gets back the 1-bit data stream that we were talking about before. And this evaluation kit basically converts that, the filters in there convert that into this readable signal that is plotted onto our PC screen. Right now, we're looking at the readout software that we actually use for the eval kit that we talked before. And this eval kit has a shunt-based current sensing module with delta sigma modulator. So right now, we're looking at the readout software that we actually use for the eval kit that we talked before. And this eval kit has a shunt-based current sensing module with delta sigma modulator connected to it. This readout software shows 3 tabs up here: the Configure tab, the Measurement tab, and the Analyze tab. In the Configure tab, we have the possibility to set the modulator clock right here. It is set to 20 megahertz. This is basically the clock that the eval kit uses to trigger the current sensing module, and the current sensing module will send a 1-bit data stream back to the eval kit with the same frequency. The filters are enabled. We will leave that the way it is. Filter type can be chosen between Sync Fast, Sync 1, Sync 3. Also this, we will leave it the way it is. The oversampling rate can be chosen between 16 and 256. Down here, you can see the shunt resistance in microohms. It is set to 522.8. Usually, we would use a lower shunt resistance in order to limit heat dissipation.
We usually use between 10 and 100 microohms max. But here, as explained before, we want to measure a small grid current, so that's why the shunt resistance has been chosen this way. The digit size in amps can be seen down here. It is 0.0036 amps. The max value are 32,768 digits plus minus, which equals 16-bit, a 16-bit resolution. If you multiply that, you will see that the maximum range here will be plus minus, I think, around 120 amps. But as said, the whole thing is a test setup here. Also, this program allows to store data to file right here. You can actually choose the file and the location here where to store. And then later on, you can analyze this data in MATLAB, for instance. Hitting set config right here, we're good to go. Switching over to the measurement tab. Here in the measurement tab, we can actually show up to 3 channels, channel 1, channel 2, channel 3. Right now we have only one module connected to channel 1. The number of measurements is the number that's actually going to be plotted. I'm going to set that to 1600. Start the measurement, and you can see the sinus curve of this grid current right here. You can also stop the measurement again and look at the characteristics of the curve. You can analyze it. What's interesting then here, we have a plot every 100,000 here, so that means 1600 measurements are actually plotted on the screen, and this is done every 100,000 measurements, means 98,400 measurements are actually discarded. Why that? This is simply for the immense number of data that we get from the module. So we don't want to plot everything here because that would be too much for our PC. Going back to the configure tab, what we can do is we can basically change the oversampling rate to 64, set config, go back to the measurement tab, start the measurement again, and you can see that we now have a much faster measurement. And in order for us to actually see the same picture, the same sinus curve, I'm going to put like 4 times more measurements on the screen, and now you can see we get the same sinus curve right here. As you can see, the noise around the sinus curve has increased, the resolution went down, but the measurement is a lot faster. Now with 64 oversampling rate, the distance between 2 measurements here on the screen is actually 3.2 microseconds. Before, with 256, it was 12.8 microseconds. You can simply calculate that by dividing the oversampling rate by the frequency of 20 megahertz. Going back to the configure tab, or let me first show you something else. Reducing the number of measurements to 200, you can see that you can actually, we zoom in a little bit and you can see the noise more in detail that we get here at the 64 oversampling rate. You can see the curve is a little more choppy here, but you have to keep in mind that we're still, have a max amplitude here of maybe 0.05 amps if you look at the left-hand axis right here. Now, if we go back and basically change the oversampling rate back to 256, go back to the measurement tab, start the measurement again, you can see that we straightened out the measurement a little bit already. The resolution has gotten better, and the choppy curve is not that choppy anymore. Now, last not least, the Analyze tab. The Analyze tab basically gives you the opportunity to analyze the frequency spectrum of your current. Right now, as we use a 50 hertz grid current, doesn't show you as much as it would if you use like a wider frequency current spectrum, but it gives you the opportunity to see noise at certain frequencies here in the spectrum. Obviously, right now, with a 50 hertz frequency, you can see that the maximum amplitude right here in the lower frequency spectrum raises up and then goes down, obviously, to minus 90 decibel right here, so it fades out for the higher frequency spectrum. But if you use a faster current that you measure, this can be quite interesting to analyze too. Now, one last thing that I want to show you, switching the filter type, our second degree of freedom, to sync 1, that config, starting the measurement again. What is interesting here, if we go actually back to our initial setting of 1,600 values, you can see that the amplitude or the sinus curve is still the same right here. So you can see that we basically look at the same sinus curve from minus 0.8 amps to plus 0.8 amps, but the resolution went down significantly. This is because we switched to a sync 1 filter, which basically goes through the iteration of integrating the signal only once, while the sync 3 does that 3 times. So the sync 1 is a little faster with getting you the result, but the resolution goes down significantly. Now, this shall be it from our little showcase right here. Now, we will go back to the presentation and have a closer look on a slide that shows a little bit more detail about what happens if you change the filter topologies.
Going to the next slide, we actually see as I mentioned before, we want to go a little bit more into detail about the characteristics if we change the filter topologies. So again, we look at a graph right here, which shows a rising edge current, the same rising edge that we saw before in the simulation. On the x-axis, again, we have our time in microseconds. On the y-axis, our arbitrary current value, and we basically plotted different filter settings here, different filter orders, and with different oversampling rates. Now, let's look at the sync 1 filters first, the red line with the sync 1 and an oversampling rate of 16, the sync 2 in yellow with an oversampling rate of 16, and the sync 3 in green with the same oversampling rate. Now, what you can see is because we increased the filter topology, the filter order, you can see that the response time goes down a little bit when we go higher in the filter order, while the sync 1 actually shows us the rising edge after, well, maybe 1.5 microseconds or something. The sync 2 already needs 2 microseconds, and the sync 3 already 2.5 microseconds. But the overshooting behavior of those filters actually smoothens out a lot if we go higher in the filter order. So the sync 3 filter, as you can see, has a very much more favorable overshooting behavior here than in comparison the sync 1 filter, which is the red line right here. Now looking at the purple line and the turquoise line down here, the sync, we can actually see a sync 3 filter with an oversampling rate of 64 and a sync 3 with an oversampling rate of 128. And there you can see we really get a lot slower right here. So it takes like up to almost 20 microseconds until we detect the rising edge. But again, the overshooting behavior of the higher oversampling rates is a lot more accurate. So as we don't have the zoom window in this picture here, you can hardly see already with the sync 364, the purple line, any overshooting behavior. And the turquoise line is actually perfectly in line here already. You would see a little bit when you zoomed in on that. Now, to summarize this last chapter, the filter setup depends on your application. So really, if you want to, for example, detect a fast overcurrent, you would go for a low filter order with a lower oversampling rate in order to be faster. If, on the other hand, you want to use the signal to control your IGBTs, you would go for a higher filter order and for a higher oversampling rate to be as accurate as possible. Using various filter settings on one-bit data stream allows an in-depth analysis of the measured current. Basically what we saw, we can use the 1-bit data stream from only one sensing module to actually apply both a fast filter that gives you the opportunity to detect overcurrents and a slower and higher resolution filter that gives you the opportunity to control your IGBT. So both is possible with only one current sensing module. So that was it from my side here. Thank you so far for your attention. My name is Matthias Hilpert. You have my contact information here on the last slide. As Latoya mentioned at the beginning, this presentation will be sent out too. Thanks again from my side, and I wish everybody a wonderful day. And yeah, feel free to contact me anytime in case questions come up afterwards. Thank you.